All right, so let's talk about this motion. Let's say there's a particle moving on the three-dimensional space, and at each time t, the position is described by this function. Okay? And the first question is, find t of t, and then b, find at and an. Now this part, I believe we did do it a few lectures ago, but let's do this again anyways. So first, you look at the velocity vector by taking the derivative, which is 2 4/3 times 3 over 2, t to the 1/2, because 3 over 2 minus 1 is 1/2. And then when you differentiate this, 2 comes down, and you get t to the first power because 2 minus 1 is 1, which gives you 2t to 1/2 power, and t. And because t, the unit tangent vector, is the normalization of the velocity vector, so you have to divide by its size. And the reason for that is because velocity vectors are always tangential to the direction of the tangential to the trajectory, and because we want a unit tangent vector, all you have to do now is to just divide by its size so that its length is a unit vector. Then it's definitely tangent and it's a unit vector, so it's a unit tangent vector. Okay. Now let's see. Therefore, this becomes 2 1/2 power is same as square root of this t, and you have to take the square root of square of 2 times radical t plus square of t, which is 2 radical t, and that's square root of 4 plus 4t plus t squared, which if you factor it, it's t plus 2 times t plus 2. If you look for two numbers that add to 4 and multiply to 4, those are 2 and 2, right? So you end up with t plus 2 times itself, which is t plus 2 squared. And 2 and square root cancel, leaving you with this as your, leaving you with 2 radical t comma t over t plus 2 as your tangential vector. Okay, that part actually we did it a couple of lectures ago. That's why I did it rather fast. But now here's the important part. What is AT and AN? This is what we call the tangential and normal part of the acceleration, right? So there's if there's the acceleration can be thought as sum of two vectors, which one is in the tangential direction, another is in the normal direction. And I explained why this is called the principal normal, because when something gets curved, that means there's a force pulling the trajectory to make it curve, right? So n is actually the normal direction to the trajectory that tells you which direction it's accelerating. So because the normal direction, the principal normal direction always points to the acceleration direction, this will always be positive. Okay? Whereas AT could be negative or positive, or could be 0, depending on whether the speed is accelerating or decelerating. So AT is responsible for speeding up or slowing down, whereas AN is responsible for how fast you're going to turn. Okay? If you turn a lot, that means AN is huge. If you turn slowly, then AN is small. Okay? All right, so this is what you get. And then you have to figure out what AT and AN are. Okay. Now, I don't think I gave you the formula for finding AT and AN, so let's think about how to get AT. So here's what you do. Suppose you have a T vector and dotted with A. What would we get? Since the acceleration vector is this thing, we can rewrite the acceleration vector as AT T plus AN N. And then we use the distributive property, which gives you AT T dot T plus AN T dot N. Okay. Then we can use the property that if you have V dot V, any vector with the self, what's that same as? I mean, for this case, it's 1, but it's a priori, it's the dot product is the norm of the first, norm of the second, which happens to be the same thing, so it's squared, and cosine of the angle between. What's the angle between these two vectors? 0. So it's cosine of 0. Do you know what cosine of 0 is? 1. So anytime you have a vector dotted with itself, it's same as its norm squared, just because of the definition of the dot product, okay? And then, what about dot products between two vectors that are perpendicular to each other?
0.
It's always 0, right? I already explained last time that if you have a tangential component, that's the unit tangent vector. That's the direction of the unit tangent vector if the trajectory is going this way. And then because it's bent this way, the normal vector will be pointing to the direction it's bending. So the normal vector is that way. And the reason you call this a normal vector is because it's always perpendicular to the trajectory. In other words, it's always perpendicular to the tangential vector. So these two vectors are perpendicular, and therefore we get that. And now, what's the norm of t? What's the size of this vector t?
1.
It's 1. Why?
It's a unit.
Because it's a unit vector. Okay. This hat here means it's a unit vector, right? Unit vector means the length of the vector is 1. So this is just 1. So you have AT, and therefore we have a very easy formula to use, which is that in order to get A of t, you simply have to take the unit tangent vector and dotted it with your acceleration vector. And since we have calculated the unit tangent vector to be this, let's just figure that out, okay? Oh, you know what? I realized I should have said something like at t equals to 3. Or else we end up with something very complicated, right? So, let's add this, okay? All right, so let's do this. How do you get the acceleration?
You
Take the derivative of
the
velocity. This was the velocity, the top part, right? Yeah, this was the norm. So let's take the derivative of the velocity. So let's see. It's dotted with, if I differentiate 2, that's 0. If I differentiate square root of t, that's what? 1 over 2 square root of t. Hopefully you memorize this. Again, square root of t differentiates to 1 over 2 square root of t. And if you differentiate t, you get 1. 2 cancels. So we're almost there. Now, therefore, AT, the tangential component when t is equal to 3, is first, I need 3 plugged in here. No, 3 plugged in here. And then dotted with 3 plugged in here. 0, 1 over square root of 3, comma 1. Okay, let's continue. this, if you plug in 3 here, it's 2, comma 2 radical 3, comma 3, dotted with 0, 1 over radical 3, 1, and then I can divide everything by 3 plus 2. I'm setting t as 3. Okay, we're almost there. 2 times 0 is 0. Dot product when your coordinates are given is performed by multiplying the corresponding components and adding them, right? So the second one is plus 2 radical 3 times 1 over radical 3 plus 3 times 1 divided by 5, because 3 plus 2 is 5. And this cancels. 2 plus 3 is 5. Oh, so it's 5 over 5, which is 1. For some reason, it became 1. It's not always true. Oh, okay, it's actually always true. For any value of t, I can see that it's always 1. That's interesting. Okay, so check that if you have time. Try to calculate.
Vector though, right?
For any value of t, you will always get 1.
Yeah, but what if your original vector was?
Oh, of course, for
2
different ones, you will be
Yeah.
different. Of course, yeah. I'm just referring to that this t equals to 3 didn't do anything. I mean, if it's always 1, you don't have to solve any questions.
Right.
Just yeah.
You like the-
Yeah, it'll be, yeah. That'll be sweet, but unfortunately, life is not that easy. Right? Calc 3 is not that easy. All right, now the next thing I want to point out is how do we figure out an then? Now, one possible way to find out an will be to do something similar. If you do n dot a, in that case, it'll be n dot t and n dot n. N dot t will be 0 this time because they're perpendicular, and n dot n will be 1, so it will give you an. So one possible formula for finding an would be doing the n dot a instead of t dot a. However, we know already how hard it is to figure out the normal vector. This requires differentiating the t. It's very ugly. We don't like that, right? So instead of doing that, what we're going to do is to use the following fact, that if you take the norm squared of this, think about it this way. If you have vector A, there's if you have some kind of curve just turning that way, we know that this is vector A. If that's given, then there's a tangential component, and also there's the normal component, right? So this is an times n vector, and this is at times t vector, and this plus this gives you this vector, right? That's the picture, right? And if you notice that these two are perpendicular, then we can just simply make use of the Pythagorean theorem, right? So what is the Pythagorean theorem for this case? It's saying that the length of the vector A, squared is same as an squared plus at squared. So it's Pythagorean theorem. In fact, anytime you have a vector into components where two axes are perpendicular, you can see that it's square of this plus square of that, the components, adding up to the square of the magnitude of the vector itself. Okay. If you have three different axes, which are all perpendicular and unit vectors, then you can take the components square them. The square sum of the components is equal to the square of the magnitude. That should always be true. Okay? So that's what I'm using. And because of this, you can use this formula to find the value of an. Why? Because an squared from this formula means it's a squared minus at squared, just by bringing this to the other side, right? Bringing this to the other side, making it a subtraction, you get that. And therefore, an is square root of norm of a squared minus the tangential component of a squared. And because we already know at, all we need to do is to take the norm of this thing. So let's take the norm of this. So let's compute a squared. What's that? That's square root of 0 squared plus 1 over square root of 3 squared plus 1 squared squared, right? And this square comes from this squared. And this square and square roots will cancel. This is 1/3 plus 1, which is 4/3. Therefore, an is square root of 4/3 minus 1 squared. Right? See, this squared is already 4/3. That's why I'm not putting a squared here. Be careful. If I had the norm of a itself as 4/3, I would have the squared, but it's a squared that's equal to 4/3, so I'm just plugging in 4/3 here, replacing the entire norm of a with the squared. Okay, and then I have at equal to 1, so I put 1 squared, which is 1/3, which is 1 over radical 3. And if you prefer, you can rationalize the denominator by multiplying by radical 3 top and bottom. So that's what you get. So that's the normal vector. So we see that the acceleration at t equals to 3 has tangential component 1, which means is it accelerating or decelerating? If at is 1, is it accelerating or decelerating?
Accelerating.
It's accelerating because it's positive. At is positive. Now, if an is some number that's not 0, is it turning or is it going straight?
Not 0, it's turning.
It's not. If it's not 0, it's turning. So it's making a turn. Well, this has to do with the curvature. You have to find the ratio between this one and the velocity, and there's something called curvature defined by using an and the velocity. But we're not going to go there. So that's all I want.